Okay. So I will continue my discussion. Yesterday, towards the end, I completed the dynamical aspects of the linear harmonic oscillator. I think it was example number 1, 2, 3, perhaps. Yeah. So the equation of motion we reduced to form omega naught square x equal to 0 subject to initial condition. And then to start with, I wrote the general solution as some a cos a is arbitrary constant, omega naught t plus some delta. So is this the general solution? Is it the general solution of this second order differential equation? Yes, because to have two independent constants. Okay? But where is the linear superposition? Linear, this is second order equation, linear superposition demands that there should be two linearly independent solutions. So where are they?
The cos can be written as e to the power something plus e to the power something.
Yeah.
E to the power I omega.
Yeah, that is one possible way. Or you expand this cos. So cos omega naught t plus delta. So how do you expand? Cos x, cos theta, cos x, cos y. So cos omega naught t into cos delta plus sin omega naught t plus sin delta, and cos delta sin delta into a. So I can write this as a cos omega naught t plus b sin omega naught t. Okay, where a is small a cos delta and b is a small a sin delta. They are two independent constants. And what are the two independent solutions? Cos omega naught t, sin omega naught t. Why they are independent, linearly independent? You calculate the Wronskian. So what is the Wronskian? It will be 1. So they are two linearly independent solutions, so most general solution. Then you look at the phase space dynamics, time series, and initial value solution of the initial value problem, which we all discussed. Now, damped linear harmonic oscillator. Of course, we also had the first integral, the energy integral, I1 equal to E is half x dot square plus half omega naught square x square. And the second integral, the time dependent integral, which I asked you to check. Okay. Now, this equation is mx double dot, so I divide by m throughout, so I get x double dot omega naught square x, or more conveniently, I write this as alpha x dot alpha prime divided by m, so that I call as alpha, the damping constant, plus omega naught square x, k by m equal to 0. Okay. So now, can you solve this equation? Can you integrate this equation? Yes, there are various methods, but can you find an integral? Well, this is a long-standing problem. Identifying an appropriate integral, or what kind of interpretation you can give, and so on. So there has been an interpretation in terms of by Bertman long back. So he interpreted this damped harmonic oscillator as kind of positive harmonic oscillator and interacting with a negative harmonic oscillator and so on, that to represent the environment and so on. But it is only in as late as 2007, in my group, my former student P.K. Chandrasekhar and M. Sendilvelan and myself, we have shown that there exists a time-independent integral for this particular oscillator case, and this has been published in JMathPhys, volume 48, 2007. This came as a surprise, time-independent integral, a damped oscillator, and this has been taken up by many people very recently. Carl Bender, C.M. Bender, is very famous for PT symmetric quantum systems et al. So again, the same journal, JMathPhys, volume 57, 2016, he has written a nice paper on that, based on this. But I will not go into the details. If anybody is interested in knowing the integrals of this, so you look into this paper. But what I will do now is to find the general solution. I am not going into the integrals because to identify an appropriate integrating factor requires some new knowledge and so on, so I will not go into the details. But you can trivially find two linearly independent solutions by look for a solution which is proportional to e power some mt. The indicial equation, try to identify an indicial equation because you have all linear terms. So you look for an appropriate m. So what is the m that you can think of? E power mt. So some a is arbitrary constant a e power mt. Try to find the possible values of m. So you get the so-called indicial equation. So what is it? M square plus alpha m plus omega naught square equal to into e power mt. So they are in general they are non-vanishing. A is non-vanishing. So this will be 0. So which means this is a quadratic in m, and m will have two possible solutions. So minus b minus alpha plus or minus root of b square alpha square minus 4 omega naught square by 2. So which you call as m1 or m2. Okay. Thus you can have general solution x equal to some a e power m1t, then or a1 e power m1t plus a2 e power m2t. And m1 and m2 have a common factor. So what is that common factor? E power minus alpha t. So you can have some constant d e power minus alpha t, then a1 e power. Now there are three possibilities. So what are the three possibilities? Alpha square greater than 4m naught, 4w omega naught square, that is over damping. Then alpha square equal to 4 omega naught square, that is critical damping, and alpha square less than 4 omega naught square, that is under damping. So alpha square less than 4 omega naught square, what do you get? This quantity becomes imaginary, pure imaginary. So you have e power I, which I will call as some I and some Ct, Ct plus A2 e power minus ICT, where C is square root of 4 omega naught square minus alpha square. Okay. So that you can rewrite as in what form? You can combine, since you have exponentials, you can combine suitably, and you can rewrite the solution as cos omega naught t and sin omega naught t. Then that is pre-multiplied by a damping term. So this is So you have the solution as x of t as e power minus alpha t, and I assume alpha to be positive, some a sin omega naught t plus a cos omega naught t plus b sin omega naught t. So these are the two linearly independent solutions, e power minus alpha t cos omega naught t and e power minus alpha t sin omega naught t, two linearly independent solutions. Then the linear superposition is also solution. Obviously this is a second order linear differential equation, so you have two linearly independent solutions. Now the initial value problem. So as before, x of 0 equal to a and x dot of 0 equal to 0, then you get the solution as maybe I will call as a prime, b prime. So you have the solution of this problem as a e power minus alpha t. No, this is not omega naught. This is c. And c equal to root of 4 omega naught square minus alpha square cos ct. And is it correct? Yeah, so I think there is a fact. Why? There is a by 2. Sorry, I have missed this alpha t by 2. And then, yeah, minus alpha t by 2. Then there is a phase factor coming in. Definite phase factor. Somehow I have missed it. So you check that. And that phase factor is tan delta. That's not arbitrary constant. It's alpha by 2c. I have missed somewhere. You can check that. Okay. So that is the solution of the initial value problem. And how does the phase trajectory look like? So it's oscillatory but damped oscillation. So how do you expect the phase trajectory will look like? So x versus t. This is t, this is x t. So you start from some initial amplitude A, and then it comes down, then the amplitude keeps decreasing, and ultimately it approaches 0. Damped oscillatory motion. It's periodic, but then the amplitude keeps on decreasing. So that is the nature of the motion. Okay. Now, next problem, 4, 5. Damped, forced oscillator. You can, the same way you can proceed. You have the homogeneous part. So I divide by m throughout. So I have alpha x dot plus omega naught square x equal to the external force, impressed forcing, applied forcing, which I take as periodic, f sin omega t. Now the frequency of the impressed force is omega, whereas natural frequency is omega naught. Okay? So these two are in general different. So what kind of solution you expect? Again, this is what kind of equation is this? This is a second order inhomogeneous equation. The homogeneous part you have already dealt with. the initial value problem, the general solution was linear sum of two linearly independent solution, and then you apply the initial condition, same initial condition you apply, then you will have this complementary function which is coming from the solution, a linearly independent solution part, and you apply the initial condition, and then there will be a particular integral. So you find this particular integral you can easily find. I will not go into the details, but for example, you can check xp equal to some a cos omega t plus b sin omega t. Substitute on both sides, left hand side, then equate the coefficients of cos omega t and sin omega t, then you will find a and b gets fixed. So you add with that part of the solution. So the general solution, without much ado, I write as except t as just the final form I will write. So I think the standard form I have here is a omega naught by c. This is just constant. This is a linear differential equation. You multiply by any constant. So omega naught by c are all fixed constant for some convenience to take care of the initial condition. You will get this. So that's not a problem. So the general solution comes as the solution of the homogeneous part, that is a omega naught by c into e power minus alpha t by 2 cos ct minus delta. So this is the solution of the homogeneous part, but this damps down, and if you wait for sufficiently long time, this will die away. Okay. But the most interesting part is the particular integral part, and that turns out to be some AP, some amplitude AP, which I will write the form, to cos omega t minus gamma. Now this part cos ct, c is I wrote as 4 omega naught square minus alpha square. So that contains the natural frequency and so on. But this particular integral part contains cos omega t, the impressed frequency. Okay. And this AP has a specific form, AP equal to the external forcing strength F divided by, anybody familiar with this? F equal to omega naught square minus omega square whole square plus alpha square omega square. So you can check, you can substitute and check, or by comparing you can find. So that is the AP, that's a fixed frequency, fixed amplitude. F, omega naught, omega, they are all given, alpha. So it's a fixed value. And then cos omega t, a periodic solution with period t equal to 2 pi by omega. So that is also fixed. The frequency is fixed. So if we wait for sufficiently long time asymptotically, the solution is just this part, oscillating with the frequency of the external impressed frequency. So the system will start resonating with the impressed frequency, impressed force. So this is the resonant periodic oscillation. So the phenomenon of resonance, it coincides with the external periodic oscillation. Okay. And this will lead to the notion of limiting periodic oscillation, the limit cycle, the notion of limit cycle. So the earlier solutions, so in the case of damped harmonic oscillator, if you look in the phase space, x dot space, phase plane, you start anywhere with a given amplitude or frequency, given amplitude, and the initial velocity is 0, then the system starts oscillating, but periodically, but its amplitude keeps on decreasing. Ultimately, it ends up with at the equilibrium point. Equilibrium in the sense that when you perturb, the system may remain at this point or it may move away. So in this case, the amplitude keeps on decreasing. So this equilibrium point, or you call as fixed point, it's an focus. The system keeps on spiraling, or spiral point or a focus point. It focuses towards that particular point. So it's a fixed point, equilibrium point. But in this case, this is for damped harmonic oscillator. For damped forced oscillator, and you can also see, even if you start from somewhere else, again it will start oscillating, and ultimately it will approach towards the equilibrium point. So change in the initial state will not affect the final state very much. So it will approach all the time towards that particular point. So here, what is the nature of the dynamics? It says, so you have x this much and x dot you can work out. And so you can start anywhere in the phase plane as the initial condition. And then you start plotting this and it approaches. But then it damps down. But finally, you got a periodic orbit with a definite amplitude. Okay. And wherever you start with, whether you start here or whether you start here, anywhere, ultimately you end up always in this periodic orbit. Even if you start inside, again the system will start approaching this particular orbit and end up finally in this limiting periodic orbit with a definite frequency t equal to 2 pi by omega. So it's a limiting periodic motion, and so this is a single curve asymptotically. This is called limit cycle, which is a unique periodic oscillator. Okay. The whole phase space compared to the linear harmonic oscillator, where you have concentric curves, one around the other. If you slightly change the amplitude, initial condition, you get another periodic curve, But here, wherever you start with, whatever be the initial state, ultimately you end up with a unique periodic orbit asymptotically for large times, and that is the limiting periodic orbit or limit cycle. So you have considered perhaps the most general kind of dynamical system, linear dynamical system. These are all correspond to linear forces, the forces which lead to dynamical equations which are linear differential equations. And the kind of motion you can think of is the equilibrium point. In the earlier case, you had concentric curves. So around the fixed point, you have closed curves. You change the initial condition, you get each one leads to a closed orbit. So this you call as a center type fixed point, and this is a spiral fixed point or a focus. And here you have an unstable fixed point, and about which the system moves away, and ultimately it ends up with a particular periodic orbit, okay, an isolated periodic orbit, a limit cycle, so a limiting periodic motion. So these are the possible dynamical state you can encounter when you have the force which leads to dynamical equation, which is the linear differential equation. Okay. So this part of the dynamics I call linear dynamics, because the underlying force leads to the dynamical equation, which is a linear differential equation, okay, simplest form. Now I consider the situation where, as I promised yesterday, to introduce some kind of more complicated force. This force, as you know, in certain cases you can also represent in terms of potential, the so-called conservative cases. How do you represent the force in terms of potential? The vector F you can express as a gradient of a scalar function. Okay, f equal to minus grad v, in which case you call as v as potential. Okay. So that the corresponding force you call as conservative forces. But I will not go into those details. You have also equivalent descriptions, the Lagrangian mechanics or Hamiltonian mechanics and so on. Well, that are additional or modified description of mechanics. Well, that again you have all studied, so I will not go into the details. Now I consider the dynamics by adding more general force. There are very many possibilities, but I will take one of the interesting kind of force that will give you a picture of what is going to happen when you introduce this kind of general force. So now, I think this is 6, an unharmonic oscillator. Earlier harmonic oscillator, now I consider an oscillator which is not harmonic, non-harmonic or unharmonic oscillator. So the simplest form I take as minus kx, the previous one, the restoring force, minus some lambda x cube. You can as well take beta x square, but for some simplicity I am taking this because it has got reflection symmetry and so on, so it will have some nicer form. So the corresponding equation of motion is mx double dot plus kx plus maybe I will take as lambda prime x cube equal to 0. So divide throughout by m. So you have x double dot plus omega naught square x plus lambda x cube equal to 0, where lambda is lambda prime by m. Okay. Now what can you say about this equation? First I ask you to check, suppose x1 of x equal to x1 of t is a solution. What does that mean? We say x equal to x1 t is a solution. You substitute this function x1 in this differential equation, it identically satisfies this equation. Okay. And let x equal to x2 of t is also a solution. Okay. And then I ask you to see whether a linear combination is also a solution. Check whether a linear combination is also a solution so that you verify the linear superposition principle. That means check whether x equal to some a arbitrary constant x1 plus b x2. Is it a possible solution? Just substitute in here and check whether it is possible. Under what condition that this will be a solution? So under what condition this will be a solution? X equal to ax1 plus bx2 will be a solution. Lambda equal to 0, obviously we already checked, that is linear superposition is valid. If lambda is not equal to a equal to, so that is the only possibility is if and only if a equal to 0 equal to b identically. The trivial solution is only possible. So the conclusion is linear superposition principle fails. So all the known techniques that you are familiar with fails. Okay. So you have to identify, so all the known functions you are familiar with cannot solve this simple equation. So you have to identify a new function if at all it's possible. Okay. You have to define a new function. Its properties may be quite different, or even if you have a more general equation, in which case it may not be possible to solve at all. Okay. So linear, first thing you note that for this kind of equation, linear superposition principle fails. Any equation, any differential equation or any difference equation or integral equation, etc., for which linear superposition principle fails is a nonlinear differential equation, because linear superposition principle fails. For all linear differential equations, it's valid, but for any nonlinear differential equation, linear superposition principle fails. Correspondingly, I call this as a nonlinear force. So, any nonlinear force and underlying dynamics I call as nonlinear dynamics. Okay. Dynamics emerging from out of nonlinear force leads to nonlinear dynamics. Okay. One consequence will be that linear superposition principle fails. You may have to find new techniques or new methods which allows you to solve this equation. Well, the Kepler problem is a typical example of a nonlinear differential equation. The Kepler problem. So what is the dynamical equation for a Kepler problem? So you have a vector, okay, a planet moving around the force field of the sun. So you have m r vector r double dot d square r by dt square equal to force, the inverse square type force, some some unit vector r divided by r cube. Okay. R, if it is unit vector r divided by r cube. Okay. So which means unit vector divided by r square. Okay. So that kind of equation, will it be linear or nonlinear? So again you apply this test. If r equal to r1t is a solution, r equal to r2t vector r2t is a solution, take a linear combination. So you will find it will never be a solution unless a and b are simultaneously 0. Okay. So it's a nonlinear differential equation. Of course, this equation you can solve, but you can solve appropriate if you find appropriate integrating factors and introduce new functions and so on and so forth, and you can get all the three Kepler's laws. So now you go back and see how you solve this problem and what kind of solutions you get and all. Okay. But now I will confine my attention only to this equation and its generalization. The unharmonic oscillator or a nonlinear oscillator. This is the simplest problem of nonlinear dynamics. Then you can go to as complex a problem like weather dynamics, which Edward Lorenz tried to understand. And now we try to solve this problem through supercomputers to predict the atmospheric weather of different places. So why it's so cool today in Kolkata and so on. So you want to predict. So you look at the Google, the weather condition Kolkata today, tomorrow, and so on. So how do people solve that? So you solve the underlying Navier-Stokes equation subject to appropriate initial conditions, and then you find the time series, and then from which you try to make predictions and so on. Now what happens to this equation? What kind of integrals this can admit? Can integrals exist? Can you identify this integral? Well, you can follow the method you used for harmonic oscillator itself. You introduce an integrating factor, x dot, multiply by this integrating factor, then you get x dot, x double dot, plus omega naught square x dot, plus lambda x dot, x cube equal to 0. Okay. Integrate once. So what do you get? X dot square by 2, then what else? Half omega naught square, x square, then 1 by 4 lambda x power 4. So that equal to I1, which I call as E or Hamiltonian electron. So there exists a first integral, as in the case of linear harmonic oscillator. Now you do a second integration. Integrate this equation. Okay. So, and then by doing a separation of variable. If you do that, as I had shown for the case of harmonic oscillator, then you will get an integration. The right hand side is just dt. Okay. So x dot square, you take 2 outside and then take all these terms to the left hand side. Okay. So you have dx by dt square, dx by dt you find, you get a square root, and then whatever it is. So you get 2e minus omega naught square x square and minus, I think, 1 by 2 lambda x power 4. And the whole problem, whole difficulty comes because you have this new term. Okay. If you do not have lambda equal to 0, this will be 2e minus omega naught square x square. So you can take a 2e by omega naught square outside and so on. You can express the solution in terms of cos inverse, sine inverse, and so on. But because of the presence of this kind of terms, you will have to define new functions. In this case, you can define new functions. But that function will have very complicated properties. So this, the defining function, there are several ways to define this function. I will not go into the details, but during 18th, 19th century, many mathematicians have defined, tried to identify appropriate functions which solve this kind of integrals. So you will have essentially integral over this. And the resultant solution you can express in terms of Jacobian elliptic functions. Or Weierstrass elliptic function. Or Riemannian theta function. Okay. So they have different notations. But I will use this Jacobian elliptic function, which now is much more easier to express. So what is this Jacobian elliptic function? I will just spend a few minutes because I'm sure none of you would have come across such elliptic function in your mathematics course, or even mathematics people do not read at this level about elliptic function. So these are called doubly periodic functions. They have one real period, one complex period. Okay? So let's not worry about this complicated stuff, etc. But what ultimately when you do this integration is, so you will have to know about this definition of elliptic function, Jacobian elliptic function or Weierstrass elliptic functions. With this Jacobian elliptic function, you have 3 kinds of Jacobian elliptic functions: Cn, Sn, Dn. These are complements of cos, sine, and then constant. Okay. So as a consequence, you have Cnu, but it is also associated with a parameter called, I think it's not confused with this, k, or I will use an m square, Snu m square, and Dnu m square. This m square can take value between 0 and 1. Okay. When m square equal to 0, m or m square equal to 0, the Cn function becomes cos of u. And Sn function becomes sine of u. And Dn function becomes 1. Okay. But when m square equal to 1, the other limit, interesting things happen. Cn becomes hyperbolic function, secant h function, secant hu. Sn becomes tan hu. And Dn becomes again secant hu. cos u, periodic with 2 pi by omega naught, okay, the standard functions. But secant HU, tan HU, what kind of functions are they? What is the period of the function secant h? What is the nature of secant h? If you plot u versus secant h, how does it look like? Secant h is hyperbolic secant h is, what is it in terms of simple function? 1 over cos HU. And what is cos HU? 1 over exponential in terms of exponential e power u plus e power minus u. Okay, cos, if e power iu plus e power minus iu by 2, secant h, so there will be a 2 also coming in. Okay. Exponential functions. So how will, when u varies from minus infinity to plus infinity, how will secant HU vary? U minus infinity. This will e power minus infinity is 0, but this will be e power plus infinity. 2 by e power plus infinity, 0. So it goes at minus u, it goes to 0. And when u equal to 0, 1. And when u equal to plus infinity, it goes to 0. Exponentially fast. So you have localized, isolated, single isolated wave. Similarly, you can check for tan H. It's kink-like solution. So this is a localized solitary wave-like solution. Solitary. The entire time axis I have written, but if it is spatial axis, in the entire space, you will have a single isolated wave, solitary wave. Okay, whereas the cos, sine, they are progressing waves, they are infinite in number with finite period. So these elliptic functions have all these properties as this parameter m square, which will depend on these quantities E, omega naught square, etc. So as they vary, then Cn can vary from cos to secant h, Sn can vary from sine to tan h, and so on. So they will have nicer properties. Okay. So in this problem, the solution is, so you will have to learn these basic properties of Jacobian elliptic functions in order to see how this solution comes about. But I will simply write the solution x of t equal to some a Cn omega t plus delta constant with the modulus square. So the m square is called modulus parameter. Ramanujan has used this modulus, Ramanujan's modular theta function, and so on and so forth. Okay, very much. So this m square, as I said, can vary between 0 and 1, depending on the value of A. Okay. Now, this omega is not just omega naught. That's the critical factor. Omega is square root of omega naught square plus lambda A square. Observe, A is the amplitude, the initial value. This initial value also occurs inside this function. As you change A, the frequency also changes. So the qualitative property of the solution is sensitive to the initial conditions. Sensitiveness to initial conditions can typically occur to initial conditions. That is the characteristic property of typical nonlinear system. There are some exceptions. I will, perhaps if I have time, I will mention. But in general, when you have a nonlinear system, the dynamics can depend on the initial conditions. And in certain case, which I will, towards the end of my talk will show, this dependence can be highly sensitive to initial conditions, in which case complex dynamics can arise, chaotic dynamics can arise. Okay. Sensitiveness to initial condition is the characteristic feature which distinguishes the nonlinear dynamics from linear dynamics. One important property. Okay. In any case, the properties of nonlinear dynamical system will depend in general on the initial conditions. How it depends, you have to identify. So each problem will have its own dependence and so on. So this is what one typically does. In this particular simple problem, it's called a Hamiltonian problem because you have a Hamiltonian, etc. It's coming in. Even in this case, this is a periodic solution. Cn is a periodic solution. All these are periodic functions. Okay, they have a real period or a complex period, but we will not go into the details. It's a periodic function. But its period has a more general property. It's not just 2 pi by omega naught. It has got a what is known as a complete elliptic integral. The period is called 4km. K is complete elliptic integral, which depends on the value of m. When m equal to 0, this will become 2 pi. 4k will become 2 pi. Okay, its property and all. But in this case, it will depend on the value of m. And this m, in this problem, again, depends on the amplitude. So m square is k lambda a square by 2 into omega naught square plus lambda a square. You see? If lambda is 0, m square is 0. So Cn becomes cos. But when lambda is non-zero, m square is non-zero. Correspondingly, omega depends on a. Initial condition dependence is shown. So these are all interrelated. Okay. The dynamics becomes more general, okay, more complicated, and so on. So the next problem, I introduced damping. So these are all realistic problems. I have not mentioned what are the possible physical system these dynamics can represent, but you can find them. I don't have time to go into the details. So I have added Kepler problem, damped harmonic, unharmonic oscillator, cubic unharmonic. So this is also called cubic unharmonic oscillator because the power is cubic. So you have equation like mx double dot plus alpha x dot, alpha prime x dot plus kx plus lambda x square equal to 0. So this problem, subject to initial condition, appropriate initial condition. Here, initial conditions were x of 0 is again 0, x dot of 0 equal to 0. And that initial condition is satisfied if you put delta equal to 0. Okay. Same initial condition. In general, there is no way to solve this problem, even at this level, except for one particular choice or two particular choices, which I have given in my book, the details of which, we have solved it some time back, and I have given the details. Okay? Only for two choices relating k and alpha or k and lambda or something like that. So you get. So in general, this cannot be solved. So I considered even more general equation, damped, forced, unharmonic oscillator. Mx double dot plus alpha prime x dot plus kx plus lambda prime x square cube equal to f sin omega t, f prime sin omega t. Again, impressed frequency omega, dividing by m throughout, I have ultimately the equation of interest is x alpha x dot plus omega naught square x plus lambda x cube equal to f sin omega t. So this is my ultimate goal, to understand the dynamics underlying this equation. So this is also called Duffing Oscillator. A Dutch physicist, Duffing, in connection with oscillations in a triode valve. So he identified this particular equation. This equation, you know, the damped forced harmonic oscillator is an LCR, forced LCR circuit, the current voltage. You have so many physical problems that's being represented by a damped forced harmonic oscillator. Similarly, this equation also represents very many physical situations. Okay. So this is a real physically interesting dynamical system. So you want to understand this dynamics. This equation itself in general cannot be solved. When you add this, obviously this is a nonlinear equation. No linear superposition principle is valid, and this is an inhomogeneous nonlinear differential equation. So you want to solve the initial value problem given the initial conditions, x of 0 equal to a and x dot of 0 equal to 0. Okay. You want to solve the initial value problem associated with this differential equation. So there is no way to solve this equation. In fact, you can see even very simple nonlinear differential equations can show the effect of initial conditions. You can even go to first order equations, very trivial equations. It's an example I will show. First order equation, nonlinear equations themselves have very many interesting systems, the so-called Riccati equations. Okay. So before that, first order nonlinear differential equation. Just simple examples. One, consider this dx by dt plus x square equal to 0, very trivial equation. If it is x equal to dx by dt plus x equal to 0, you know how to solve it. It's a trivial equation. Now x square equal to 0, you can still solve it. Isn't so? Dx by x square equal to dx by x square equal to minus dt, or whatever it is. So you solve this, x of t equal to 1 over t minus t naught. Is that okay? So just differentiate, you will have minus 1 over t by t naught square and plus, so that will satisfy it. So what do you observe here? If you extend this solution in the complex t plane, this solution characteristically depends on the initial value. T naught is the integration constant, the initial value, because the value you give depends on the initial condition, and this is the arbitrary condition that appears. And your solution depends on, and it can become singular at because T naught can be placed anywhere in the complex plane. Okay. At some point it will become singular. So this is a pole, singular. It's a singularity. Now you consider dx by dt plus x cube equal to 0. So you find the solution x of t is some constant of or something like that, square root of t minus t naught. singular algebraic branch point. Algebraic branch, movable. So these are all called movable singularities. Can appear typically even simplest of differential equations. So that shows that once you have a nonlinear differential equation, initial condition can play a crucial role, even simplest of differential equations. You can consider many other equations. You can consider movable essential singularity and so on. In fact, during the beginning of the 20th century, French mathematicians, particularly Paul Painlevé and his co-workers, have tried to classify first order, second order differential equations as per the nature of the movable critical singular points they exhibit. So Painlevé and co-workers have identified first order differential equations, those equations which are free from so-called movable critical singularities. Critical singularities are those singularities which are branch points and essential singular points. Movable poles are allowed critical points. Okay? So the Riccati equation, so I'm sorry I'm telling many facts, but it's interesting to know Riccati equation. Riccati equation specific form is dx by dt plus some RT of x plus qt of x square equal to some gt. Okay. So this equation is called Riccati equation. So this equation, whose movable singular points will be only poles. Okay. If you add x cube, etc., they will have movable critical singularities, that is movable branch points, essential singular points, and so on. Similarly, if you consider second order differential equations, Painlevé and co-workers have identified 44 different classes of second order differential equations which will be free from movable critical singular points. And then they have identified, including equations which admit elliptic functions. But they identified 6 characteristic new equations. These are called Painlevé transcendental equations. I cannot write the forms. Painlevé transcendental equations. So they require the definition of new functions, transcendental functions, Painlevé transcendental functions, defining Painlevé transcendental equations. Okay. So these 50 equations, 44 plus 6 equations are supposed to be free from movable critical singular points. All the other second order differential equations will have movable critical points. Now the problem has been further extended in recent times to consider third order and third order. So one way to look at nonlinear dynamical problem is to look at the structure of movable critical singularities. That is one mathematical way of looking at these dynamical equations. But if you consider, for example, this equation, we have investigated this some time back. It shows very, very complex structure of singular points and so on. So that is an indication that the problem is not integrable, and if at all you want to study the properties and the real time, you have to go for numerical integration. Okay. There is no analytic methods, as far as we know, to solve this simple second order differential equation exactly. Okay. So you try to look for numerical analysis. So in my next 5 minutes or so, I will simply flash through some of the understanding that we have when we try to integrate this equation numerically. I will not go into the details. Yeah. So this is the elliptic function you have, which I wrote, and the linear harmonic oscillator satisfy linear superposition, but unharmonic oscillator will not satisfy. And as I showed the damped harmonic oscillator, you have the focus singular point. Wherever you start, ultimately you end up at the focus point. But even if you choose a different initial condition, ultimately you end up with the same singular point. Whereas for the forced damped oscillator, whether you start inside or outside this isolated periodic motion, you always end up in this big circle. So, limiting cycle motion. So, that is the resonant periodic oscillation. So, when you have this unharmonic oscillator, you have these elliptic functions solutions. With damped oscillations, yes, you cannot solve, but damped forced oscillations, this is what the dynamics. Well, you can consider this problem plus omega naught square minus omega naught square. Well, this minus omega naught square is called double well problem, but as far as the dynamics is concerned, that's more interesting, because if you have minus omega naught square, you will have 3 fixed points on the real axis, and it has some interesting symmetry properties, and also normally one goes one analyze that problem, but plus sign also is an interesting problem. But here what I try to show is how the dynamics behaves as a function of external parameters. We call them as control parameters, because these parameters are in your control. You see, there are 5 parameters: the damping constant, this natural frequency, this is nonlinear restoring force constant, external forcing amplitude, and its frequency. So, this is a second order differential equation. You can scale away 2 quantities. You can change x to some ax, t to some bt, and then remove 2 of these constants. So, ultimately there will be 3 independent constants in this problem. You can choose any of those 3 constants. So, normally we choose alpha, beta, and f, because omega naught square is a fixed value, and so you change alpha, beta, f, or alpha, beta, and omega, or whatever it is. Okay. In this particular figures, I change only one parameter, f, external forcing strength, which is very easy to change, because if you have an appropriate circuit, it is the external forcing, external voltage, strength. So, I change. So, I ask by numerical integration, so Ranjukutta 4th order, for example, you try to solve this differential equation. So, start from F0. I ask the question, how does the dynamics change as you change F? When F equal to 0, obviously it is a damped unharmonic oscillator. Whether it is a linear oscillator, non-linear oscillator, ultimately it is the damping which will overtake. So, ultimately the system will end up in one of the equilibrium points. There are 3 equilibrium points, one on the left side and the center and on the right side. So, I choose the initial condition such that it ends up in this fixed point. Okay. That is when f equal to 0. Now, we change the value of f, okay, 0.1, 0.2, and so on. For example, I have shown the phase plane picture for f equal to 0.33. So, what I get is, if I omit the initial transients, what we call as initial, how the system, if you start somewhere initially, then it will ultimately end up. So, finally, asymptotically for large time, what you get is this closed orbit. So, what does it imply? I said in the phase plane, if you have a closed orbit, it corresponds to a periodic motion, and you have only one closed orbit. So, it is specific period, and this period will be equal to the period of, one period we call period t. Okay. So, that is a limit cycle motion, okay, single limit cycle. Now, as you change f, typically there are typical values, maybe I will list that out for your convenience. So, these are all numerical studies. You can never do an analytic study of these values. Yeah. So, typically up to 0.347, 3437, up to 4 decimals, if you do that, you get the same qualitative picture. Then something strange happens if you cross this 0.347. For example, at f equal to 0.35, you find a curve which overlaps with the previous closed curve. Actually, if you see that, it takes twice the earlier time. So the period now suddenly becomes twice that of this curve. So you say it's a period 2t periodic oscillation. Okay. Period doubles. Well, this continues qualitatively until you reach the value f equal to 0.355. At 0.356556, again sudden quality change. Instead of period 2, this becomes period 4, 2 power 2. Again period doubles dramatically. And this continues until f equal to 0.3577. Small change, finite change. At f equal to 0.377, then the period becomes again doubled, 2 power 3, 8, period 8, then period 16, period 32, and so on. Ultimately, at f equal to 0.3589, it becomes infinite. So to come back to the same value, it has to execute infinite time. So at that stage, the system becomes chaotic, extremely sensitive to initial conditions. And then as you continue, it becomes more and more complicated. This I can put figuratively in a so-called bifurcation diagram. So you see that at every value of f, you have a periodic motion. So you can cut this periodic motion, okay, and note down the point, the maximum amplitude. So what I have plotted here is for every value of f, the corresponding maximum value of x. So until f equal to 0.3437, you have just one maximum value, that means period 1. But then at that critical value, you have two possible values like this. So this period 2, then period 4, period 8, etc., in very narrow range. And this change, at critical change, occurs in a particular ratio. It's called Feigenbaum's ratio, universal ratio, and so on. Ultimately, here you find there are infinite possible values. And this is an enlarged version of this region. Okay. Period doubling, route to chaos. So what does this chaos means? In that region where you have this infinite time that takes, infinite possible number of points that occur, this is what happens. So you integrate the dynamical equation starting from an initial value. So this is a time axis in some normalized unit. This is the value of x. And you are looking for bounded motion. So you start from that initial condition. There are two curves. One is blue and the other one is orange. Okay. So I start this blue curve. I start at this initial value. And then I follow this system. It is not periodic. It is aperiodic. That's why you get the infinite curve, complex curve. So periodic. But since it's a bounded system, it has to come. The system is bounded between minus 1.5 to plus 1.5. So it varies in this range. So it periodically it changes as time progresses. That is the blue curve. But what I do next is I start from an initial condition which is extremely close to the previous one. In the 4th decimal or 5th decimal, there is a small change. Then I plot the resultant curve, time trajectory, in this orange color. So actually I have drawn this, but blue and orange, they coincide, so you don't see the difference for some time, some finite time. But then you see somewhere here, you see they separate out. There is a deviation. And then it again goes back, but then you find if you come for a characteristic time, 40 or 50 time units, these two separate out and the deviation is as large as the system size itself. And since the motion has to be bounded, they again reduces but again increases. But if you calculate the average deviation, they exponentially diverge. So this shows, this is a measure of extreme sensitivity to initial condition. What means? It means even if you change the initial condition very slightly, the final behavior, final difference will be very large. Small changes can lead to very large changes in finite time. That is the important thing, not in infinite time. So that is what Henry Poincaré predicted in his studies on three-body problem as early as 1900s. Small changes can lead to very large changes. And you see in a very simple dynamical system the occurrence of such a possibility. And that occurs not for every value of f, but in certain range of f, this can happen. Okay? So beyond this value f equal to 0.3589 and so on, this complexity can arise. And then if you start looking at this region, you see there are some gaps. It is very complicated. There are some gaps where you can have periodic motion, where you can have other kinds of bifurcations. So this is period doubling bifurcation to chaos, but in between there could be quasi-periodic root and other roots, etc. So this problem is not completely analyzed even now. Because numerical analysis, you can change this parameter only in finite ranges, finite values. So you can change this, the fourth decimal, you can change in the fifth decimal, you can change in the eighth decimal. New features can arise. So the problem, understanding the nonlinear dynamical problem is never complete. In these regions, the dynamics is regular, no complexity. They are only periodic motion. But in these regions, for critical values f, complexity arises. Now you change beta also simultaneously. You change alpha also simultaneously. In three-dimensional parameter space, you try to study the dynamics. It is going to be extremely complex. Very simple dynamical system can show very complex behavior. I think I have taken more. I think I have, I have crossed that by 15 minutes. So this is what makes the study of nonlinear dynamics extremely interesting, fascinating, and so on. Okay. And if you start doing this, you can ask the question, well, this is how quantitatively you measure this deviation, etc. You can introduce the so-called Lyapunov exponent. So in these periodic regions, they have negative value, but in this chaotic regime, they take positive value and so on. In between, there are regions where you have negative values, etc. That shows periodic orbit. But you can ask the question, if you couple, when single oscillator shows that complex behavior, if you couple many such oscillators, what could be the dynamics and so on? Obviously, the dynamics is going to be much more complicated. But then, typically you find when you have many such oscillators, the system can exhibit very coherent motion. Complex, I mean chaotic, but still orderly structure, so-called synchronization. I think Dr. Shamik Gupta is an expert on this synchronization, notion of synchronization and so on. But from a different point of view, if you try to study what happens if oscillators gets coupled, linear oscillators plus linear coupling, I'm sure in your classical mechanics course you have the notion of normal mode decomposition, energy sharing, etc. But if you have nonlinear coupling or nonlinear force, what happens? This is what Fermi, all of you know Fermi, and along with two mathematicians, computer scientists and mathematicians, Pasta and Ulam, in early 1950s at Los Alamos National Laboratory. He posed this question under different circumstance. So Fermi, Pasta and Ulam. Well, there is a big story behind all these studies. I am out of time, and this was never published, but it was available as an internal report, Los Alamos internal report, which showed results which was against the basic principles of statistical mechanics. So that questioned the basic law of statistical mechanics, namely equipartition theorem. So you know that in classical mechanics, when you have large number of statistical mechanics, when you have large number of dynamical systems, when they interact, Then if you wait for sufficiently long time during interaction, for example, in this room 10 power 23 molecules or atoms, they collide, give away, take away energy and so on. If you wait for sufficiently long time, there will be equilibrium, statistical equilibrium emerging. So the temperature, the pressure, etc., they reach an equilibrium value. Thermodynamic equilibrium results in. But these people found in this particular problem, coupled oscillator, this never happened. This is what the famous Fermi-Pasta-Ulam dynamics of a chain of weakly coupled nonlinear oscillator. Just one-dimensional chain. Consider the Newton's equation of motion. Nearest neighbor couplings. Linear coupling Y, but nonlinear forcing also. If you consider such a nonlinear forcing, they found dramatic. This is what is called FPU, Fermi-Pasta-Ulam recurrence phenomena. This particular figure has shook the foundations of modern physics. Okay. It showed. So what is shown? I just take a minute. This picture shows this 32, 64 or 128 oscillators coupled through unharmonic force. You give an initial energy distribution, initial condition. You give all the energy, most of the energy to the first mode and all the other modes up to 32 or 64 or 128 oscillators. They have very little energy. You allow them to interact and then evolve. You find, as expected, energies, the first mode is given to the second, third, etc. There is an energy sharing, but if you wait for a characteristic recurrence time, the initial states come back. The initial energy comes back to the first mode and all the other modes lose. And this keeps on recurring. Even now, this problem is again and again being investigated with supercomputers and all. Situation is exactly similar. Why such a phenomena occurs? And the consequence of which, if you go to the continuum limit, you are familiar with linear waves, but this particular problem under appropriate circumstance leads to what is known as a nonlinear partial differential equation, Quatermack-Debris equation. Again, there is a big history behind this. I cannot go into the details. If you want, you can read this book for some details. This function again admits elliptic functions, a limiting form of which is the secant h square function. Okay, secant h square function. And because these people, Martin Kruskal and Naban Zabisky, they took up a periodic boundary condition, and they find that you start with an initial condition which is half of a cosine wave, and as you wait, numerically integrate, at that point was not completely solved, it's numerical integration. At finite time you get this dot curve, but if you wait for sufficiently long time, you get a series of pulses like the secant h wave form. But these secant h functions have the interesting property. The amplitude, the velocity, they are directly proportional to each other. That means the larger the wave, the larger the amplitude, the larger the velocity, and vice versa, which never takes place, can happen in the case of ordinary linear waves. And as a consequence, the larger wave, there is a number of finite pulse-like waves of secant h square type. This larger one will travel faster, will soon catch up with the smaller one. But after catching up, interacting, it comes out without change of form or diminution of speed, and it appears here because of periodic boundary condition, re-emerges here. Like this. Two waves, they collide, finite time. After collision, they come out without change of form or diminution of speed. Particle-like collision, solitary wave undergoing collision, so they are called solitons. So another phase of nonlinear dynamics is that they can exhibit completely stable solitary-like structures called solitons. So that is the new physics, integrable systems, completely integrable infinite dimensional dynamical systems. So these are two phases of nonlinear dynamics, chaos and integrability. So which system will be chaotic, which system will be integrable, and so on. So these are some of the interesting questions that are being asked being investigated by many, many people. So that leads to possibility of very many interesting results being identified in future. So I do hope some of the young people like you will take up some of these challenging problems in future and come out with some fascinating results in future. I wish you all the best. Thank you very much. So if you have any questions, comments, I have taken much more time than allotted, but I'll be happy to answer any questions. Please. Yeah, so m square, you have an elliptic function. So once you have an elliptic function, it's characterized by a parameter called modulus square. Depending on this value of this parameter, it can be just standard periodic waves like sine, cosine. If k square equal to m square equal to 0, Cn becomes cos, and the period will be 2 pi by omega naught. Okay. If it is 1, it becomes an isolated solitary wave, secant h. Just the entire time you will have just a single pulse. In between, you will have waves which is neither 2 pi by omega naught nor infinite, so in between some values. Depending on m square, the period of the wave will be for capital K, the complete elliptic integral, which is a function of m square. So this capital K will take different values depending on this value of the modulus square parameter. Okay. So the modulus parameter you see is also a function of the initial condition. Okay. And this nonlinearity parameter. Okay. So depending on the nonlinearity, its value of the nonlinearity parameter and the initial value, the m square will take a value. Correspondingly, the form of the periodic function will change. Okay. So that is the nature of nonlinearity. So any other question? That is simplest one you can choose, okay, because I mean, it's called stroboscoping mapping. So you ask your computer to note the value whenever it reaches the maximum. You can take any other values. There's no need that it should be the maximum value. So, but maximum value you can easily identify. Okay, so that's the. Yeah, please. Yeah. Yeah. So depending on if I take instead of plus omega naught square, if I put a minus omega naught square, then you will have a function like Sn dn. So depending on the form of the differential equation, you can get other functions also. There is interrelationship between these various functions. So, for example, you have Cn square u plus Sn square u equal to 1. Similarly, Cn square u plus k square dn square, I think u equal to something, it's 1 or k square or something like that. So there are interrelationship between these three functions, so that will play a crucial role. So solitary type is in some sense periodic with period infinite. Okay. Just single isolated wave. Okay. That is, for other values of m square, you have a number of waves. But that number is maximum when m square is 0. phonons are solutions of linear wave equations. The solitons have the remarkable property when they collide with another solitary wave, it retains its shape and speed except for the phase shift. So in that sense, it's a stable entity, physical stable entity.
Maybe they can view those videos, no, of solitary waves and
The colliding, yeah.
how it was discovered.
Yeah. Well, I cannot go into the story, but it's, yeah, that is a very interesting story. Some details of which we have given in the book, so you can read that. How solitary wave, for example, can be identified with the 2004 December tsunami, how you can represent that in terms of Korteweg-Debris equation. Like that, there are many, many other equations, nonlinear partial differential equations, or even coupled ordinary differential equations, which can exhibit such solitary waves, solitons, and so on. So that's another challenging area in which nonlinear dynamics evolves.
Sir, in the Duffing Oscillator, where you shown the phase portraits, and the value of A is equal to 0.365, you can just go back to the slide. And there are two phase portraits corresponding to the value, the last value.
Yeah.
The bottom two pictures.
Yeah. So here, this complex kinetic behavior is centered around this fixed point. But then there is a jump to other equilibrium point. So if you cross F, if you exceed F, this particular value, it goes to the other fixed point.
The value of A is unchanged here. So
Yeah, F is a constant value, but still it's sufficiently large, it can jump to the other fixed point.
depending on initial conditions.
It's not only the initial condition, the value of F. And then if you increase F further, it can cover both the equilibrium points. Double band, this is called single band chaos, this is another single band chaos, and then you will get double band chaos and so on. So there are regions, if you look at this bifurcation diagram, you will see that it covers both the regions and so on. So in this region, you have extremely complex dynamics, okay, and interspersed by periodic behavior and new kinds of bifurcation. So if you try to enlarge these regions, etc., you get even much more complicated bifurcation diagram and so on. So in that sense, I always feel even this problem is not completely understood. There are many, many new features you can always identify if you have sufficient patience to investigate this. And then in the 3-parameter space. Okay. Yeah.
So this transition is in terms of time, like
No,
for
no.
some time it is like this, and then at some point it jumps over to the other.
No, this is function of F. So if,
No, suppose I do that.
what is that? Well, I don't.
I think that's what you are
Yeah.
asking, right? That,
Is that same value? Maybe. Yeah, it could be. Yes, for some time it could be. So that is double band chaos, I think. Yeah, for the same value. Yeah, for some time it's around this, and for some time it's this. Yeah,
keep
you're correct.
observing the system, it is here, and then
Yeah.
some point it is
Yeah.
then it goes
Yeah.
back and
Correct. Yeah, thanks.
And for all these diagrams, apart from the first one, the initial transients are excluded.
Yeah.
By the way, so I forgot to mention that he has this book and there's another one. So this book is available in our library, so you may download it if you want. Nowadays you download books rather than issue books from the library. Whichever form you want, you may get very good description or discussion on nonlinear dynamics.
Yeah, so whatever I have discussed in the first couple of chapters, I have given the details, but you can get more details about the history and all, nature of solitons.
So if there are no further questions, let's thank Professor Lakshmanan for two very beautiful and insightful lectures.